So, I hope some of you are starting to tune in. Hope you're doing okay. I know it's a difficult time, but I'm going to try to teach you some statistics so at least you have that to go with you when you go off to college. So, the last model I want to look at with the normal distribution is the binomial model. And the cool thing about the binomial model is binomial means just like a bicycle, there's two outcomes. There's either success or failure. So the easiest way to think about success is in terms of your probability of it happening. So if I say that there's an 80% chance, let's say there's an 80% chance of there being sun today, there's a 20% chance of no sun. Right? So there's only two outcomes. You either have sun or no sun, right? So we would call this P, our probability of it happening would be zero point 0.8, and the probability of it not happening would be zero point 0.2. So the thing about a binomial distribution is P and Q always have to add up to 1. Okay, so whatever you're looking for, the thing, if it doesn't happen, that's the rest of the probability. And the nice thing about a binomial distribution is we can use a normal model as soon as long as some conditions are applied. The first is n times p and n times q both have to be greater than 5. So the probability of success, they both have to be greater than 5. And if both of those conditions, if that condition is met and it is binomial, then we can use a normal model. So let's look at an example. 13% of the population are said to be left-handed. If we were in class, we would actually be testing this by asking people who's left-handed, but there's a 13% chance that somebody will need a left-handed desk if they're in a college classroom. Left-handed desks open up the opposite direction. If you're left-handed and you've been in a college classroom, you know what I'm talking about. Your chances of having someone who's left-handed taking your survey is 13%. And the chances of having someone that's not left-handed take your survey is 87%, because that's the rest of the population. 13 and 87 add up to 100. If we have a binomial distribution with n number of trials, and the number of successes, the probability of success is P and the probability of failure is Q. And I've told you that n times P and n times Q are both greater than 5. A normal model can be used, and this is the cool thing. The mean is n times P, and the standard deviation is the following formula: square root of n times P times Q. So we're going to practice with that. So in a sample of 100 people, does a normal model for the binomial distribution apply? And we're going to sketch the curve. So we're going to check a couple things here. So first of all, we know n is 100. We know P is 0.13. And we know Q is 0.87. So we want to check n times P. So that's going to be 100 times 0.13, which is 13. And we're going to check n times Q, which is 100 times 0.87, which is 87. Well, both of these are larger than 5. So that's a check. Also, we have a probability of success and failure, so that's our second check. So we can use our model. Now our model, you recall, when we use normal model, we need to know the mean. So the mean in this case for the binomial model is n times p, and the standard deviation is the square root of n times p times q. So we already have our mean here. Our mean is 13. So what is our standard deviation going to be? So let's use our calculator. So this is from algebra. We're going to use second square root, 0.13 times 0.87 times 100. And we get 3.36. So that's my standard deviation. Come on, Microsoft, come back to me. This is my Wi-Fi in the living room isn't so great, so I've got to wait for it to come back. There we go. All right, 3.36 is my n times p times q, so that ended up being 3 is my standard deviation. So the standard deviation for this model comes out to be the square root of 0.13 times 0.87 times 100, which ended up being 3.36. So if we wanted to sketch that model, the middle of the model is going to be the mean. So the average number of people we would expect out of 100 to be 13. And if we start adding 3.87 to the right and subtracting 3.87 to the left, we would end up getting our model, right? So this would represent 68%, 95%, and 99.7%. So it's normally distributed where the mean is 13 and the standard deviation is 3.36. Okay. If I wanted to draw one standard deviation, this would be what, 16.36. And if I had 3.36 again, this is going to be what, 19.72, and so on. It's like we did with other distributions. So what is the probability that there will be no more than 15 people in the sample who are left-handed? So 15, if you look at this picture here, is going to be somewhere around right here. So no more than 15. So we want to know what's the probability that this happens. If we want to know what's the probability that there are more than 15, then what's the probability that there are no more than 15? So that means 15 or less, right? So that's going to be this side, right? So I'm going to, I don't know if I can get rid of that right part. There we go, right? So 15 or less. So we want to know what is the probability that X, or in this case, since we're using a binomial model, the probability that our observed value for P is less than 15. We could actually just use, this is, we're not using, you don't know this, but we're not using proportions, so we're just going to call it X. And if you recall, it's just a normal CDF where the lowest amount of people you could have in the class is 0, the most we want is 15, the mean is 13, and the standard deviation is 3.36. 0, 15. So second bars, you can use normal CDF from 0 to 15, and the average amount of left-handed people in a group of 100 is 13, and it's 3.36. And so my probability of there being no more than 15 people in the class is 0.724, which is a 72.4% chance of that happening. Okay, that there be no more than 15 people in the class. So the next part of this example says, what's the probability that there will be no more than 11 people wow, I just made a mistake. So I read this one incorrectly, so it's a really easy fix. If I look here, it says, what's the probability that there will be more than 15 people? So the easy fix to this is I solved for the left-hand side. So if there's a 72% chance that there be 15 or less, then all I have to do is subtract from 100, and I'm going to get 27.6%. Right, so it's important that you read, and in this case, I read that incorrectly. Actually, I ended up solving for what I had originally drawn, which was 15 or more, right? So this should have been a normal CDF from 15 to, let's say 100, because that's the most people there are in the class, and the standard deviation was 13 and 3.36. And if you put that in the calculator, you get 0.276, which is 27.6%. So important that we read the question, or I read the question. All right, so let's look at the next one. The reason I cut that is because the next one is actually asking for 11 or less. So in this case, we want to know what's the probability that there are 11 or fewer people in the class who are left-handed. And so if we're looking at our plot, it's going to be to the left of the mean. So it's going to be somewhere around right here. This is 11. The mean was 13. So somewhere to the left. So again, we would have normal CDF. And in this case, from 0 up to 11, the mean is 13, and the standard deviation is 3.36, I believe. So if we go to 11, and the mean is 13. Oops. 13 and 3.36. So 0.2758. So this comes out to be 0.2758, which is very similar to the previous example, 27.58%. Right, so that is our first look at the binomial distribution. And I will come back and do a video of the next part.